What I want to talk about in this lesson is the idea of the atomic radius. So, atomic radius. So, if we think about an atom, for example, so an atom we have the nucleus, and then outside this nucleus we have electrons, and they move around in regions of space. Okay, so what we're trying to figure out then is how far or what is the distance between the nucleus, let's say, and the outermost electron. So imagine this here is the outer, or what's known as valence electron. So it's the outermost edge, if you like, of the atom. Now, the problem with this is that when we think about electrons, electrons do not just follow, they don't just hang out in a very specific space all the time. What they're constantly doing is they're constantly moving in and out. And even as you go further and further out, let's say, from the edge of an atom, what you can actually find is there still is a probability of finding an electron out here sometimes, some of the time, maybe not all the time. So therefore, um, it's not easy to define, let's say, a clear border of where the electrons of one atom ends and where the electrons of another atom starts. But nonetheless, what we have to do is we have to try and come up with some way at coming up with what's known as the atomic radius. So what we do, or what's done in order to kind of overcome this, is we look at, let's say, we have two atoms of hydrogen, let's say. So this is hydrogen 1 bonded to hydrogen 2. Now these here could be any atoms. But let's say we're just saying two hydrogen atoms and they're bonded together. What we can do then is we can actually measure the bond length. So we can measure the distance from the nucleus of one atom to the nucleus of another atom. And we call this bond length. And we can use X-rays to measure bond length. Now, what we have here then is just an official, let's say, definition of what we mean by atomic radius. So the atomic radius of an element, so an element, for example, hydrogen, is half the distance between the nuclei of two atoms. Now, this is the bond length from here to here. If we want to talk about then the atomic radius, which is what we're interested in, it's half of the bond length. So it's half the distance between here and here. So it's half the distance between the nuclei of two atoms of the element that are joined together by a single covalent bond. Now remember, you can have different types of bonds. So for example, you can have carbon and it can be double bonded, and you can also have carbon that has a triple bond, like so, where it has it's sharing 3 pairs of electrons, whereas here it's sharing 2 pairs of electrons. But what we always want to look at when we're looking at bond length, we want to look at a single covalent bond. And remember, a covalent bond is where an atom shares 2 electrons between each other so that it can have a full outer shell. So that's what we're interested in. So this here then is a way at figuring out this, what's known as atomic radius. And what we have here, if we look down here, what we have is it's the table of atomic radius for the first 36 elements on the periodic table. And these measurements here are in what are known as nanometers. So nanometers. So we can see here the various different bond lengths. And just to put into context how small a nanometer is, if you were to take, for example, if this was a human hair, for example, so human hair is roughly, it's about 100,000 nanometers thick. So if you think about the size of a human hair, it's extremely, extremely small. And if you think of the thickness, the width of it, you're talking about 1,000 nanometers. And if you have a look here, so if we think about the radius, if you have two, so let's say we have a hydrogen atom bonded to another hydrogen atom, So this distance here, if we wanted to measure from here to here, you're talking, this is 0.037 nanometers. And if you look at that in comparison to the width of a human hair, it just gives you an idea of how small these radiuses actually are. Now, what we can notice here as well is that there's some particular trends that happen in relation to the atomic radius. So as we can see, so here we have some of the elements, so some of the group 1 elements. Now what actually starts to happen is as you move down the group, so these are group 1 elements. So as you start to move down this group, what you'll notice is that the radius, it actually increases. So as you move down, the radius increases as you move down the group. As you can see, as you move across the group, like this, so let's say if you stick it with this period here, and you move across, what you'll actually notice is that the radius decreases. So what we want to do is we want to kind of look at some of these characteristic or trends of the size of the radius of atoms and try and explain why this happens and what's causing this to happen. So what we want to think is then, like, what is it that causes these particular trends to happen? So if we have a look at what happens when we move down a group. Okay, so what we have here, so we have two atoms, so these are all group 1 elements. So these are group 1. The first group on the periodic table. Now, all of these group 1 elements, their very outermost electron or their valence electron in each of the atoms that make up these particular elements, what you'll notice is that they have one electron in the outermost energy level or the outermost shell. So you can see here, so you have lithium, it has this one electron here, and you have sodium, and it has this one outer electron. But what we notice is that sodium has a bigger radius than lithium, for example. So if you were to measure the distance from here to here, and you were to measure the distance from here to here, lithium is going to have the bigger radius. So what we want to try and understand is, why is this the case? So what you'll notice as well is that, so we have two different effects that start to affect lithium and sodium. And what these two things do is they actually impact on the size of the radius. So the two things you have are, so number one, you have the number of energy levels occupied. That's one, the number of energy levels occupied. And then the other one is this thing that's known as the screening effect. So the number of energy levels that are occupied and the screening effect. So what we mean then by the number of energy levels occupied, if we take lithium, for example, so there's two energy levels and the two energy levels are occupied. Now, if you think about like what's between the nucleus and the outermost electron, there's one energy level in lithium. Now, sodium has two energy levels, so N is 1 and N is 2, that are fully occupied between the nucleus and its outermost electron. So therefore, as a result of that, because it has more electrons, the radius of sodium is going to be bigger. And as you move down this group, what starts to happen is you get more and more energy levels that are occupied between the nucleus and between the outermost electron. And as a result of that, what we can see here on this trend here, and it also shows the same thing here as well, as the atomic number, so the atomic number, remember, comes from, so the atomic number is the number, so it's the number of protons. The number of protons that are present within the nucleus of the atom. So as you move down the group, what starts to happen is we start to get more and more protons within the nucleus of the atom. And as a result of that, we have more and more electrons as well. So as the atomic number increases, what starts to happen is as you move down a group, the atomic radius starts to increase. Now, also as you move down the group, what's starting to happen as well is that you're getting more, the number of energy levels that are occupied by electrons also increases as well. And this is what causes the nucleus to be, or the radius to increase. And as you can see here, so lithium, for example, so these are just representations of the radius, the size of each of these atoms of these particular elements. As you move down the group, you see that they start to increase. Now, also what we have then as well is this, what's known as the screening effect. So a way to kind of think about that is, if we think about the nucleus of the atom, it's generally positive. So it's made up of two subatomic particles. You have protons and then you also have neutrons. The protons are positively charged. So what they do is they exert a force. The nucleus, or these positively charged, this positive charge that comes from the nucleus has an effect, or it has a pull, if you like, on the negatively charged electrons. So what we call this, we call it nuclear charge. So you have this nuclear charge. So nuclear charge. And you can also have charge, so you have nuclear charge that's effective. So you can call it effective nuclear charge. And what does that mean? So imagine there's no, so this is our negatively charged electron. There's nothing, let's say there's nothing in between the nuclear charge, the positive charge, and this negatively charged electron out here. If there's nothing between this, then we can say that basically this electron is feeling the full effects, or 100% of the effects from the nuclear charge. But the minute you start putting things in between this, so let's say if you have another electron here, what starts to happen is the force that's exerted by this positive charge, it starts to reduce. So the effective nuclear charge starts to reduce. And as a result of that, this electron out here on the outermost, like on the very outermost or valence electrons in atoms, it's not going to feel the full pull of the nucleus. And as a result of that, it'll be freer, if you like, it'll be freer to move out this way. And this charge here wants to kind of pull it in this way, but because it's out here, and because you have this other negative charge that's essentially getting in the way, or screening the effects of the positive nuclear charge from the nucleus, as a result of that, this electron on the outside here, it doesn't feel as much of the pull from this inner nucleus. And as a result of that, it's a little bit freer, so it is. Now what we can see here is, if we have a look back here then, so if we take lithium here, for example, you're going to have the effective nuclear charge coming from the protons that are within the nucleus, and they're going to be pulling on this outer electron and pulling it in this way. But what's going to happen is these negatively charged electrons that are occupying the first energy level, they're going to exert, they're negatively charged as well, and as a result of that, they're going to repel. So imagine this is a negatively charged electron, and this is the other negatively charged electron. So these are going to repel. They're actually going to repel each other. So this is going to want to push this way, and this is going to want to go it's going to want to go the opposite way, like so. So what's actually happening here then is you're getting this screening effect that's happening. So the more energy levels that are occupied between the nuclear charge that's coming from the protons within the nucleus and the outermost electrons, the more energy levels that are between these two actors, if you like, what happens is the atomic radius actually starts to get bigger, because this, if you like, the positive charge of the nucleus can't pull the electron in as close to it as it wants to, because what's happening is these guys here are acting as a screen and they're pushing it out the way, whereas the nucleus is pulling them in the way, this is pushing them out the way. And as a result of that, the more of these occupied energy levels you have that have more, that are more full with negatively charged electrons, you get more of this, what's known as a screening effect. It starts to push, it pushes the outermost electrons out away from the nucleus, and as a result of that you get a bigger radius on the nucleus. So that's what starts to happen as you move down a group. So as you move down a group, you get more energy levels that are occupied. You get, so this increases, and this also increases as well. But what happens if you stay on, let's say, one particular energy, if you stay on one particular period and you move, let's say, horizontally across, if you move across the periodic table, what starts to happen in relation to the atomic radius? So what we can see here then is that as you move across a period, so instead of moving, so you're moving across a period on the periodic table, the atomic radius actually starts to get smaller. So what we can see here is that even though the atomic number is getting bigger, so as you move from left to right across the periodic table, the number of protons that are present in each subsequent atom is increasing. But what we notice here is that the size of the atomic radius is decreasing. So for example, we can see here, if we start off with sodium, it has an atomic radius of 0.16. And then if we end up down here with chlorine, it has an atomic radius below 0.1 nanometers. So what's actually starting to happen here, and why is this starting to happen? Well, what's actually starting to happen here is that imagine this is our nucleus, and you have a positive nuclear charge here. Now what actually starts to happen is as you start to move across the period, you start to get, so they all have the same, so they're going to have the same, let's say, number of energy levels occupied, but the number of, so they're going to have the same number of energy levels occupied. So for example, they all have the same energy level that's occupied, so they have the same number of, let's say, screens of electrons between the inner positive charge of the nucleus and the outer negative charge of the electron. But what's actually starting to happen is as you move from left to right, the number of protons is increasing, and if the number of protons increases, what happens is the nuclear charge increases, but also then as well the screening effect stays the same, because we have the same number of energy levels that are occupied. But as a result of that, so if this, for example, if this here stays the same, the screening effect stays the same, and if the nuclear charge increases, what's going to happen is this outer electron here is going to feel more and more of a pull inwards. And the more and more of a pull inwards it feels, the smaller and smaller the atomic radius starts to get. So essentially what starts to happen is it starts to reduce. So what we can say is that trends in the size of the atomic radius on going across a period depends on a number of factors. So number one is the nuclear charge. So this nuclear charge. The atomic radius decreases on going from left to right across a period because the increase in nuclear charge, which exerts a greater attractive force on the outer electrons. So as you move from here to here, the number of protons increases. With the number of protons increases, the nuclear charge, or the effective nuclear charge, increases as well. And as a result of that, these outer electrons start to feel more of a pull inwards. And as a result of that, what happens is you start to get these reduced nuclear radii as you move across, because the outer electron, or the outer boundary of the atom, starts to feel a greater pull in towards the nucleus. Now also as well, the screening effect, so within the same, when you're on the same period, the screening effect within, within the same energy level, so basically what happens is all of these, they're within the same energy level, within the same energy level, the screening effect by inner levels is the same, because there's the same number of inner levels. So as you move across these, from left to right, for example, across a period, the number of electrons between the nucleus and the outer electron, it's the same. So there might be one or two, for example, energy levels or occupied energy levels between the outer electron and the inner electron, and as a result of that, this stays the same. So there isn't anything that's counteracting the increase in the pull inwards from the increase in nuclear charge, from the increased number of protons as you move across. So these two factors, this increase in nuclear charge and the screening effect from the electrons between the outer electron and the nucleus, this stays the same. And as a result of that, what starts to happen is you start to see this trend here, like we see here. The atomic number starts to, as we move from left to right, and the atomic number increases, the number of protons we have increases, but the radius actually starts to get smaller and smaller and smaller, and it's because of these two effects that are happening. So hopefully that makes sense. And so that's basically atomic orbitals and the factors that affect the size of these, atomic radius, and the trends that you see on the periodic table in relation to the radius of the atoms. So thank you for listening.